3D printing is a fast-growing technology that has driven significant advances in many fields of science. In the areas of tissue engineering and regenerative medicine, this technology has shown potential to shorten the drug developing time, reduce or eliminate animal testing, personalize therapies, and even someday replace damaged or deteriorated tissue and organs for fully functional artificial ones. Complex microstructures are one of the signatures of nature. The inner architecture of a material dictates its functionality and determines its application. The fabrication of complex structures at the micro and nanoscale is still a critical challenge in bioengineering, and many systems have been developed to print biomaterials at high resolutions. But this is often hard to achieve and too expensive. At the Alvarez and Trujillo Lab, one of our contributions to the field of biofabrications is the invention of chaotic 3D printing, which is a technique that allows us to generate complex, multi-layer, and multi-material structures in a short time and at a low cost. Biomaterials are necessary for the bioprinting and biofabrication of tissue models. Hydrogels are polymeric networks commonly used for these purposes. They resemble many of the characteristics of human tissue, such as the capability to retain amounts of water. The hydrogels we use is called gelatin methacrylate, or GELMA. The device we work with is called mini journal bearing. A 3D printed structure holds two stepper motors in place. These, aided by the electronic and mechanical components shown in this video, control the velocity, direction, and a degree of rotation of two independent cylinders. The inner cylinder is placed inside the hollow external cylinder and works as a mixing shaft, and the external functions as the reservoir. The space between the walls of the cylinder will delimit the printing area. The inner wall of the external cylinder and the external wall of the inner cylinder interact with the liquid. The device allows for two arrangements, the concentric and the eccentric. If both cylinders are located concentrically, the flow generated will be regular and the resulting microstructure will be even and generated linearly. However, if the cylinders are located eccentrically, the system will experience chaotic flows, which will generate microstructures at an exponential rate. The printing protocols that we follow have a strong mathematical foundation, chaos theory. Our process is carried out in cycles, which are composed of the rotations of the two cylinders in opposite directions, first the internal and then the external. The degree of the rotations of each cylinder and the amount of completed cycles determines the figure that will be generated. The result is predictable and can be mathematically modeled using the Navier-Stokes equation. This system can be used for many applications. In order to fabricate fibers, we will fill the reservoir with glycerin, place a drop of GELMA on top of it, then we activate the device for a given amount of cycles. The difference in densities between both materials will maintain the hydrogel on the surface during the whole process, and will allow for the formation of a single fiber. After this, we expose our fiber to UV light, which will cross-link our hydrogel, and we can remove the shaft and reservoir to recover the fiber. Chaotic 3D printing is a powerful and cost-effective tool that is capable of producing complex structures at a high resolution in a short time through an iterative process that has a strong mathematical foundation that helps us mimic what nature does.